Welcome. Here we resume our discussion on geometric optics, and as advertised that we will continue with the refraction, that is the law of refraction, but we first need to introduce the idea of refraction. And after having done so, we will talk about Snell's law, that's another name for the law of refraction. And then finally, we will see an amazing phenomenon which is determined experimentally. That is the total internal reflection of light. Okay, with that outline out of the way, we're ready to begin. So remember, in our earlier discussion, we said that there are three ways that light could go from the source to its destination. The first one was that it could go about this flight directly. It could go directly from the source to the destination, and we concluded that this was not the most interesting case. And then we went on to consider the situation where light goes from the source to the destination, but in the process it changes direction by means of reflection. So reflection primarily for us we will refer to it as a change in direction, but remaining in the same medium. So that is light simply changes direction, but it still remains in the medium in which it travels. For instance, when light gets reflected on a mirror, it makes its way to the mirror through a medium of air, but when it gets reflected, it's reflected back into that medium, so it doesn't get transferred or it doesn't permeate a medium, it doesn't change medium, it remains in air. So that was the case in the situation when we were considering reflection. Now we're going to consider refraction. Here there's not only the change in the direction of the light rays direction, but there's also the change of a medium through which the light ray is traveling. Let's talk about it a little more formally. Formally, we say that the changing of a light ray's direction whenever it passes through different medium, which are made of matter, is known as refraction. So this is what we mean when we talk about refraction. We're talking about the changing of the direction of light by virtue of it going from one medium to another. Over here I have constructed a demonstration where we have one medium, I'll call it medium 1, and I've indicated it with a blue hue. And over here I have medium 2, represented with the red hue. The light ray initially is traveling inside of the blue medium, medium 1. However, when it reaches this interface, because it's changing media, notice its path of flight. Instead of maintaining the expected straight direction, it changes direction. Some people refer to refraction as a bending of light. That's not preferred because this is also a bending of light. That's a curved kind of a bending. It's better to refer to this kind of to refer to refraction as a change in the light, in the direction of light of a light ray. That's much better, as a change in the direction of a light ray. Of course, bending is occurring here, but the word bending is a little more loaded and could potentially lead us to a misconception. Okay, so over here, this light ray, instead of maintaining a straightward path as light rays do, or rays do. Remember, rays are straight lines that are issuing from some kind of a point source. So expected here is that the light ray would keep a straight path. However, because of the change of medium, that path gets changed. Now, is there a law that governs this phenomenon? Remember, when light was changing direction but remaining in the same medium, we had the law of reflection. And we said the angle of incidence is equal to the angle of reflection. Now, in this situation, is there some kind of a phenomenon that explains, or rather a law that explains this phenomenon? Well, before we get there, it is useful for us to first talk about the speed of light. So we were going to make a detour and consider the speed of light. So Einstein told us that the cosmic speed limit in the universe is the speed of light as measured in a vacuum. That is 3.0 times 10 to the power 8 meters per second. That's about 300,000 kilometers per second. That is the fastest anything can ever zoom by in the universe. The speed limit of, the speed of light is the upper limit. Everything else has to travel at a speed less than that. This is the universally accepted value of the speed of light. However, it must be noted that this refers to the speed of light in a vacuum. When light is propagating through a medium, typically it travels at a speed less than this 3.0 times 10 to the power 8 meters per second. The reason it does so is because light interacts with the atoms of the medium. Obviously, every medium is made out of some kind of a material, and because light is interacting with the atoms of the medium, it therefore will travel slightly less than this vacuum speed. Actually, as an example, the speed of light in fresh water is not 3.0 times 10 to the power 8, but rather it's approximately 2.25056 times 10 to the power 8. As I've mentioned before, that light travels slower through a medium because it's interacting with the atoms of the material out of which the medium is made. The stronger the interaction of these atoms with light, the slower light will move through that medium. The weaker that interaction is between light and the atoms that make up the medium, the faster light will travel through that medium. Now, suppose the speed of light through some medium, I'm going to call it medium A. Suppose the speed of light in this medium is referred to as VA. Then we know that the speed of light in that medium will always be less than the speed of light in a vacuum. That is, V sub A will always be less than C. C is the standard symbol we use for the speed of light. If you might recall, E equals to mc squared, that c squared is the speed of light. Okay, again, the speed of light in any medium will always be less than the speed of light in a vacuum. This allows us to define a ratio. This ratio is known as an index of refraction. The index of refraction is defined as the ratio of the speed of light in a vacuum divided by the speed of light in that particular medium. It is worth noting, or to specify explicitly, that the index of refraction is a property of a medium. So glass will have its own index of refraction, and water will have its own index of refraction. Oil will have its own index of refraction. So this is a property of the medium. And that means this property of the medium will indicate to us at what speed light would propagate through that medium if it were to do so. And just for mathematical interests and also for future notes, this inequality, the fact that VA will always be less than the speed of light, implies to us that the index of refraction, remember C divided by VA, is nothing more than N sub A. Again, n sub a, the index of refraction, will always be larger than 1. Indices of refraction are always larger than 1 because the speed VA is always smaller than the speed of light in a vacuum. This idea of the index of refraction is a worthy detour because it enables us to describe this phenomenon we observed earlier on. And it allows us to speak of the law that governs this phenomenon. So it's a worthwhile detour. However, before we get there, it's good for us to get comfortable with how to understand and how to use this index of refraction. So we're going to first talk about an example. Experimentally, it has been determined that the index of refraction of NaCl, sodium chloride, is equal to 1.544. So sodium chloride is crystalline, so when you shine light through some crystal of some kind of of this salt, you will find that light will travel at a speed less than that. What is the speed at which light travels through sodium chloride crystals? Well, since we know the index of refraction and its definition, we can reshuffle this definition and make the speed of light through the sodium chloride to be the subject of this formula, and we end up with something like this. We know the speed of light through vacuum, that is the known 3.0 times 10 to the power 8 meters per second. I should say this is meters per second. And the index of refraction is 1.544. This therefore means that the speed at which light travels through a sodium chloride crystal is given by 1.944 times 10 to the power 8 meters per second. It's worth emphasizing also that the index of refraction never has a unit. It's unitless. Consider how it's defined. The speed of light has units of meters per second, and the speed at which light moves through that particular medium is also has units of meters per second, so those units would cancel out. Although it's obvious, but it's worth highlighting. Let's consider a second example where we could use the index of refraction definition the other way. Suppose this time around we're given the speed of light in the medium and we're interested in determining the index of refraction of that medium. Then we could use this in a straightforward way. That is, we know the speed of light in a vacuum, that's c, and we are given the speed of light through that medium, that's v. In this case, the medium is fresh water, H2O. And by plugging in these values, we can deduce that the index of refraction of water is 1.333. Again, without units because this ratio is unitless. Okay, hopefully this gives us a bit of an idea of how to exploit and how to use the idea of an index of refraction. Now we're in a good position to begin to talk about the law that governs refraction. So then this brings us to Snell's law. So we have two media. One is medium 1 with a particular index of refraction. And we also have a second medium with a different index of refraction. When light travels and changes media, the law that governs this interaction is known as Snell's law, and it is given by this. That is, the index of refraction of the first medium times the sine of the angle of incidence is equal to the index of the second medium times the sine of the angle of refraction. It's worthwhile to spend time to think about what this means. One of the helpful things to do in order to help you understand what this means is to contrast it with the law of reflection. The law of reflection says that the angle of incidence is equal to the angle of reflection. So these angles are directly equal. However, with the law of refraction, these angles are not directly equal to one another, but it is the sine of the angles times the index of refraction, or times the indices of refractions that are equal. So the equality is at this level, not at the level of the angles themselves. Okay. Then let's consider an example how this applies. Here we have a light ray. This light ray emerges from a sodium chloride crystal, and we've learned that the sodium chloride crystal has an index of refraction given by 1.544. This light ray emerges from the NaCl crystal and it enters fresh water, whose index of refraction is given by 1.333. Now, if the angle at which if the angle of incidence, that is this angle here, is equal to 20 degrees, what is the angle of refraction? What is the angle of refraction in the second medium, that is water? Well, this is where we used Snell's law. This basically tells us that, Snell's law, which tells us that this is how the angles are related. They're not directly related, but they're related through the sine function and the index of refraction. If we're to shuffle this formula around and make sine theta 2 the subject of the formula, we will end up with this. And the index of refraction of the first medium, NaCl, is 1.544, and that of fresh water is 1.333, and the angle of incidence we said was 20 degrees, and you plug these numbers in a calculator, we find that this is equal to, well, sine theta 2 is equals to 0.39705, which if we take the inverse of this, we will find that theta 2 is equals to 23.44. I should emphasize that this picture here is not drawn to scale. So my point is this angle here clearly does not correspond to 23.44. This is one of the pitfalls that students sometimes fall into. They might take the illustration as the literal. I commend you be careful that sometimes the pictures are just to illustrate the statement. They are not to be considered to be drawn to scale. And this is testimony of that. Okay. Alrighty, I hope this example gives you a bit of a handle on how to employ Snell's law. Now, thus far, we have been treating the refraction alone. But in real life, the actual case is that whenever light is traveling and it changes medium, typically it's not that refraction is the only thing that happens. Typically you find that there's also some light rays are reflected while others are refracted. You might imagine when you're driving and maybe you're looking in your windshield, you might see yourself reflection. On the one hand, the light from you is exiting the car because people can see you outside the car. But also you see yourself. So part of the light is reflected. So the typical actual situation is that part of the light rays are reflected back and some are transmitted, hence refracted. Now we're going to begin to consider What happens when you change this angle of incidence? And that's the job of the next slide. As we change the angle of incidence, the angle of refraction also changes. As we increase this angle, make it larger and larger, there comes a point which is determined experimentally, which was first discovered experimentally. There comes a point where when you increase the angle of incidence, you find that the angle of refraction is equal to 90 degrees. That is, the transmitted light ray makes an angle of 90 with the normal line. At that point, that angle of incidence, which corresponds to this 90-degree angle of refraction, is known as the critical angle. Put in another way, a little more clearer, is that the angle of incidence for which the angle of refraction is 90 degrees is known as the critical angle. So the critical angle here implies that the angle of refraction is 90 degrees. How can we determine this angle, this critical angle? Well, since we know the angle of refraction is 90 degrees, we could go back to Snell's law and plug in theta 2 to be 90 degrees and determine what theta c should be. Theta c, if we do so, this as outlined, we find that theta c is given by the arc sine of n2, that is the index of refraction of the destination medium, divided by n1, which is the index of refraction of the source medium. And the critical angle will always depend on the media. What kind of media are you working with? The reason why it depends on the media because it's defined in terms of the indices of refraction, but the indices of refraction depend on the type of media you're working with. So it is worth knowing and emphasizing again that the index of refraction between NaCl and water will be different for when we're dealing with air and the vacuum, or vacuum and water, or water and let's say ethanol, for instance. So my point is, this theta c, the value of it will always depend on the media at play. Now suppose we were to push our boundary. Suppose this were the theta c, that is the critical angle. What happens when we go beyond that point? What happens when we shine the light at an angle larger than the critical angle? We know at the critical angle, when we shine light at the critical angle, we know that the reflected ray is going to make an angle of 90 degrees. But what happens when we go beyond? Well, when we go beyond, we find that all the light gets reflected back to the medium. No light gets transmitted anymore into the second medium, but all the light gets reflected back. Notice in this case, we still had some light being transmitted into the second medium and some reflected. But in this situation, when we go beyond the critical angle, no light makes it to the second medium. All of it gets reflected back. This phenomenon is known as total internal reflection. I should emphasize that even if this were made of glass, even if this medium were transparent, when we go beyond the critical angle, all the light gets reflected. This need not be a mirror of some sort, or actually, even if this were a transparent medium, when you exceed the critical angle, the refracted rays all become reflected. Nothing makes it out anymore. Actually, this is exactly how fiber optics work. You have light that is trapped, that is kept inside of a clear tube, which is the fiber. Because of this phenomenon, total internal reflection, although the tube might be transparent, the light ray simply is contained inside. It's simply contained inside. And because this is a light ray, the speed of light is much faster than the speed of electrons in a copper wire. Your copper wire, that's what is used in ADSL on your internet. That's quite quick, but your fiber optic, your internet, internet is provided through fiber optics. That's much faster than your ADSL. So this is one application that is quite close to your heart and your daily experience of total internal reflection. For further details and filling in any things that are not clear, I commend you to this section of our OpenStax book. And we will stop here, and I will supply you with exercises for you to practice. Thank you.